Welcome everyone to Astronomy on Tap. I am Dr. Cameron Hummels. I am the computational astronomer at Caltech, who is emceeing your event for tonight. Thank you all for joining us. We have a really cool event, and Astronomy on Tap is back. So welcome back, friends. Sorry there was a hiatus since, since June, I think. The rough schedule for tonight is I'll give a couple of announcements for over the next few minutes, and then we will have two 15 or so minute presentations given by local researchers on their science, which is super interesting, followed by like 5 to 10 minutes of Q&A for each one. And finally, for the final hour or so of this event, it'll be pub trivia, astronomy themed pub trivia, which is usually super fun. And in fact, it'll be interactive. You all can go to a website that I'll introduce in a bit called Mentimeter, menti.com, and you can enter your answers to our pub trivia questions into the website or into the app on your phone, and then it'll show up live for us to see how everyone is responding. So there is interactivity. Unfortunately, there are no prizes. I'm not going to ship cool prizes to you. I don't have a budget for this. So knowledge will be your prize, and we can all be the better for it. So let's see, a couple of quick announcements. We have another Astronomy on Tap next Monday at this, well, no, it's a little bit earlier. It will be at 5 p.m. and it will be entirely in Spanish, and it will be themed on the coming launch of the James Webb Space Telescope. So we will have two scientists who each have early science time on the first cycle of science observations that will be taken with James Webb, who will be giving presentations about their research. One will be a new postdoc here at Caltech named Dr. Sofia Gallego, talking about galaxy evolution. And we will also have Dr. Geronimo Villanueva from Goddard Space Flight Center in the NASA Center in Maryland, who will be talking about exoplanets. So it should be really cool. But again, that's entirely in Spanish language. So I encourage you to get the word out to, if you yourself speak Spanish, or you know people who are interested in astronomy and space science and speak Spanish, I encourage you to get the word out to them. And then we'll have an event the week after that, another Astronomy on Tap, that will also be about James Webb, but it'll be back to being in English. And it will be all about the James Webb launch and the solar system and exoplanet science that it will be performing. And then we'll have another James Webb event in December as well, but it'll be focused on larger scale stuff, galaxies and large scale structure and stuff in the distant universe. So should be really cool, but I'll post all of those on our YouTube site in the next few days, and then you'll be able to click on them and on our Facebook page and so on and so forth. Okay, so for tonight, again, the rough schedule is 15-minute talk, 5 to 10 minutes of questions, 15-minute talk, 5 to 10 minutes of questions, and then about an hour's worth of pub trivia. Because Astronomy on Tap is traditionally held in a bar, I encourage those of you who are of age to imbibe, to take advantage of this opportunity to have a beverage of your choice while hearing about science. I need to go grab a beer. I will do that in the next few moments. But it's super fun, it's laid back, and it's a good opportunity to relax and hear about science. So Julie, can you turn on your camera and your microphone and join me?
Hello.
Welcome. Hello, how are you?
Good, very good. How are you?
I'm okay. Well, what is that in the background? Are you truly in Yosemite right now?
No, I'm at home. Fortunately or unfortunately, no, that's raining right now. But yeah, it's a good picture.
I see. Yeah, that is a good picture. Oh no, noises. Sorry, I always get so mixed up trying to make this work remotely. Okay, so are you drinking a beverage? I'm going to go grab a beer, but
I am. I have. I guess you can't see. That's just the glass though. So what's in it is ginger ale and bourbon.
Oh, that's a favorite of mine. I love
Yeah.
that one.
Yeah, I like it.
I actually met Julie. She's a world-class mountain biker, in addition to being a world-class scientist. So, have you been cycling much in the same games?
Yeah, I've been away from my bike over the past couple of months. Yeah, I bike over the weekend. It was nice, nice weather. It's getting a little cooler here
Yeah, it's
in
nice.
LA. So
Lots of rain today. We definitely need it. I feel like this is the most rain we've had in like 2 years now.
yes, I think so.
Okay, I will now introduce you. So, Dr. Julie Belrose obtained her PhD at the University of Michigan, studying the dynamics of binary asteroid systems and spacecraft applications. She's been a navigation engineer at the Jet Propulsion Laboratory, the NASA Center, since 2013, and she is the navigation chief for DART, the Double Asteroid Redirection Test Mission. In her free time, she goes on bike rides and hikes with her dog. Yeah, I'm really excited to learn more about DART. When does it launch? When is it supposed to launch?
Next month, in like 28 days.
Oh, wow. Okay. So
Yeah.
thank you for taking time in this critical lead up to the launch time. But yeah, I'm really excited to learn more about this and what the future of us being able to push asteroids around will be. So I'll let you go ahead and share your screen and take it away.
Okay. Thank you for the introduction and this opportunity. Let me share my screen. There you go. All right. And let's make that the presentation. There you go. Hope everybody is seeing the same as me. So I'll be talking about DART. That's short for Double Asteroid Redirection Test. This is a mission that I've been working on for the past couple of years. I think it started formally maybe 3 or 4 years ago. It's a mission that's managed by the Applied Physics Lab in Maryland. So it's not actually a JPL mission, but we've been contracted out to do the navigation, and I'm the nav chief of that effort. So it's a NASA mission handled by the APL lab, and we take a little part to it. So as we just mentioned, I guess, the launch is next month. At least the launch periods start next month. So DART could launch in a time frame of between November 24th and February 15 of next year. So about 90 days worth of opportunity, and it's one opportunity per day. It's a night launch, and it's going to be out of Vandenberg, just 3 hours north of LA. So if you're in the city, you can try to get on some higher ground, and you should actually see, if it's not too cloudy, you should actually see the launch that night out of Vandenberg. So we're launching this spacecraft on a direct collision with a binary asteroid called Didymos. So that's kind of what you see there with the two asteroids. Let's see, the mission is a short mission. It's about 10 months long, and the impact is it's going to be somewhere between September 26th and October 1st of next year. So it just depends when we launch. So if we launch on November 24th, then we'll hit on September 26th, and then February 15 as a hit of October 1st, 2022. So we targeting this binary asteroid, and it's named Didymos. And we're going to impact the smaller guy, Dimorphos. So a binary asteroids, if you've never heard of that, is basically two asteroids that orbit each other. So it's kind of like a mini Earth-Moon system. So you have the bigger asteroids here, Didymos, that's about a bit less than 800 meters. It has its own spin rate, and then it has a little asteroids that orbiting around it. That's Dimorphos here, around 160 meters, and it takes almost 12 hours to go a full orbit around the bigger asteroid. And so DART, as I said, we're launching it in a direct impact. So on September 26, 2022, it's going to hit Dimorphos. It's about 650 kilos, including the fuel. And it's going to hit the asteroid as about 15,000 miles per hour. So we're not slowing down. We're not accelerating, but we're not slowing down. And that's about a bit less than 7 kilometers per second. So it's going to be pretty exciting next year. And so we're doing that to be able to measure the change in the period of the smaller asteroids around the bigger asteroids. And I'll talk about more about the planetary defense aspect of that a little later. So let's see. Other thing that's interesting on this mission is we're carrying a little CubeSat called LishiQ. That's a contribution from the Italians, and it's like a 6U CubeSat, and we're gonna release it at about 10 days before impact, and basically it will be not too far from DART, and they'll be able to observe the dust, the plume from the impact. And so when we'll impact this asteroid, it's actually going to be pretty close to Earth. So it'll be about 7 million miles away, which is relatively close. And so we'll use some Earth-based telescope to be able to measure the change in the orbit period of the small asteroids with respect to the bigger one. And so why do we bother to go to a double asteroid instead of a single asteroid? So I have this here. So you can see here, Dimorphos has a orbit around the bigger asteroid. So we'll be impacting it. That's going to make a new orbit. If we do that at a smaller scale like that of a binary asteroids, then it's much easier to measure. So we've, with the spacecraft mass and the velocity, we calculated that we'll change the orbital period by about 1%. And so that's about 10 minutes. And so in the weeks after, or the months or the weeks after the mission is done, if everything goes well and we actually hit, then we'll be able to detect about 10 minutes and change. And so if we were doing the same experiment for an asteroid that was going around the sun, a single asteroid, then we would need to measure the change in orbit around the sun. And so for the same kinetic impact, then that's much harder. And so that small change of the orbit period about the sun, that's about 6 times 10 to the minus 6%. And so that would take many years to detect. Let's see, whoops, what do I do? There you go. So I put this table here. So that's some interesting facts about the Didymos system. So it's binary asteroids that was first detected in 1996. If you were to, plot all these orbital elements, you would see that the orbit is, come close to Earth at perihelion, and then at this furthest distance from the sun, it's just a little further from Mars. So it's kind of going in and out of the Mars orbit, if you want, and come close to Earth at about every couple of years. And so let's see, I've mentioned a lot of that information. The distance between the two asteroids is about 1.2 kilometers. So it's pretty small. And you have system mass and density. So there you go. I've put that there also because you might need it for the trivia if you stay long enough on on this with us. To give you an idea of the scale that we're talking about, how big are those asteroids and the spacecraft compared to some known features on Earth. Then you see the DART spacecraft here. It's fairly small. It's kind of a 2 meter by 2 meter box, but it has some long solar array that I'll explain why in a couple of slides. And so it's about almost 20 meters in length. And so if you compare that to a bus, then it's just a little longer than a bus. And then Dimorphos here, about 160 meter. And so that's, you see the comparison here, I guess, with the Statue of Liberty. And then Didymos here, bigger than the Trade Center, and I guess not as high as, I think that's probably one of the tallest building on Earth, the Burj Khalifa. Oops. So the spacecraft, so this is actually how it looks like. It's a cartoon, and it has some long solar arrays. It's a tech demo mission basically for planetary defense. It's NASA's first tech demo mission, but it has a lot of new technology on it that that NASA wanted to test, and that will kind of be infused in some future mission. And so it that's what mostly drove the design of the spacecraft for this mission, not so much the planetary defense aspect of it. And so I have a kind of a more blocky diagrammy slide here. And basically, it's a very simple spacecraft. We're carrying a camera. So that's kind of the one major instrument, most important instrument that we're carrying. And the camera is basically a big telescope. So we'll be able to detect the asteroids at about 1 month out, so 1 month before impact. And we'll be using that for 2 parts. So one part is, so we're doing navigation for the spacecraft. And so basically during or along the trajectory, we'll be getting some Doppler and range data using some pretty big telescope we have on Earth, part of the Deep Space Network. And so we'll be calculating where the spacecraft is going. And at some point, we need to figure out where the asteroid is so that we can actually, aim towards it. Otherwise, basically, we're just aiming in the void. So we're using the images from the camera in the last month to, if you want, augment that orbit determination effort and be able to maneuver the spacecraft to aim towards the asteroid. And at about 4 hours before impact, then the spacecraft has basically an autonomous navigation system, and it's going to be on its own and aim for the spacecraft. So it's going to differentiate between the 2 asteroids and aim towards the smaller asteroid. So that's our most important instrument. We have the little CubeSat here that you see and mentioned from, that's a contribution or work with the Italians. And then other than that, it kind of has some basic functionalities, some thrusters so that, we can maneuver around. It has a high gain antenna, also low gain antenna, those small little arms here that you see, that's 2 low gain antenna, and high gain antenna. So then we can stream the images, especially towards the end. That's just a lot of data that we need to downlink. And so we'll be using the high gain antenna. That's also a new type of high gain antenna. And then this year is an ion propulsion system. And so that's basically why we need those big giant solar arrays, because that requires a lot of power. I think it requires about 5 kilowatt power. And so that's to test this next generation of propulsion system that uses xenon. Basically, like it ionizes the xenon and electrostatically accelerates the ion, and so that acceleration makes a push, and we can use that as to change the trajectory over kind of a longer period of time compared to more like chemical thrusters that have a higher impulse or higher, so that's on the spacecraft. And then and so how does DART fit in this planetary defense effort or strategy that maybe you've been hearing about here and there over the past probably couple of decades? Basically, that planetary defense involves a lot of different things. So there's, we need to detect what's out there. So there's some space-based and ground-based observation that's doing that. We need to characterize what's out there. And so there's, different type of observation platform that quantify what's out there or classify them and kind of assess the threat this way. There's different coordination groups internationally, and then there's different activities that are done to try to mitigate or find some solution to potential small body threat, asteroids or comets. And so DART is the first full-scale flight demonstration of an asteroid deflection technology, and that uses kinetic impact. So a high-speed impact on an asteroid. There's a lot of different solution out there. Probably the three most popular one are either a kinetic impact, using a nuclear device, or using what's called a gravity tractor, where you have a big spacecraft mass, beside an asteroid, and it kind of uses the mutual attraction to slowly steer the asteroid. And so DART is the first kinetic impact demonstrator, and it's to test the ability to achieve a kinetic impact, and also test how a real asteroid responds to a kinetic impact. There you go. So we have my dog here. He wants to walk. And
cool. Everybody loves dogs.
Yeah.
Can we see your dog?
Oh yeah, she's here. There you go. There you go.
Hello.
Say hi.
Hello,
She's like, oh my God. And so here's my last slide. And so DART is part of a more bigger international collaboration called IDA. And so it evolves over the past decade somewhat. But so DART is the first kinetic impact demonstrator. It has this LiCube on board, and then there's a European mission that that's going to be launched in 2024 if everything goes well, and that's an orbiter that is going to go to the Didymos and orbit the system. So no kinetic impact for that one, but it's going to orbit the system, get kind of a final measure on that orbit change between the two asteroids, and get the more precise mass of the two asteroids. So that should coming up in I guess that might be a few years, and it's going to get there in 2026, I believe. So that's pretty much what I have. Thanks for your attention, and then I welcome any question. There you go. All right, thanks.
Excellent, excellent. Super interesting mission. Thank you for the presentation, Julie. So yeah, we encourage people to ask questions. There have already been a few asked in the YouTube chat, but go ahead and ask questions if you have them about the mission or about the asteroid or whatnot. I have a question. So it separates, it slams its the bulk of it into the orbiting. So it's a binary asteroid, right? So you've got Didymos, and what's the other little guy?
Dimorphos.
Dimorphos. So it slams part of the DART mission, runs into that at whatever, 6 kilometers per second, which is really fast.
It's quite fast, yeah.
It changes the dynamics and changes the orbit. And then the other chunk is just sitting up there taking photographs and trying to analyze what's going on. Do we know, asteroids, some asteroids are monolithic, like a single rock, and others are rubble piles that are just kind of loosely held together. Do we know that Didymos or Dimorphos are one or the other? Because it might have a really different impact if you slam something into a bunch of rocks that are only loosely held together versus if you slam them into like a single stone.
Yeah. So the different scientists that have kind of studied more that system in particular seems to think that it's more, a rubble pile that's, held together as opposed to like a big solid chunk. So that's why when a spacecraft, when DART's going to hit, they expect some kind of plume, and then the little CubeSat will be able to observe that and kind of quantify a little more the structure of the asteroid and how efficient the impact was, depending on how much of that happened.
Will the CubeSat also be able to do science about asteroids, like the composition of it and stuff, or is that left for Hera in the future to be able to do that? Because obviously I realize the point of this is like, how well can you hit it and change its trajectory? But there's also like cool science stuff to be done about the composition of asteroids.
Oh yeah, for sure. There's a lot of different science that you can do, especially if you stay a longer time. So I think Hera will definitely do some of that in a more precise way, perhaps. The CubeSat will basically just it'll be released, but this spacecraft is going at almost 7 kilometers per second relative to the asteroid, and so it's going to be ejected, but it's basically going to follow the same speed. It's just going to be a little off to the side, and so it's going to take some pictures, but then it's going to fly by and just keep on going. There's nothing to stop it, and it doesn't have a big propulsion system to make that big of a break. So it's not going to stay around for very long. But the combination of that set of pictures and then DART will basically stream some images all the way to, I think, like the last few seconds. And so it'll have some very close images, and they'll be able to tell pretty much exactly where it hit. And so that combined, and then after that, the measurement from Earth-based telescope, they can put all that together and kind of, answer a lot of the questions. And then after that, a lot of, the remainder of the questions, hopefully that's going to be answered by Hera.
Cool. Okay. Enough me hogging the Q&A with my own questions. Let's see. There was a question, what launch vehicle is being used to put this up?
That's a good question. It's the Falcon 9.
One of the SpaceX guys.
Yeah, it's a SpaceX rocket, Falcon 9. So we've been working with SpaceX since the past, 2 years. It's very exciting that they're on board.
But it'll be Cape Canaveral or Vandenberg or?
Vandenberg, yeah.
Okay.
So spacecraft is already at Vandenberg now. I think, the boosters are already back from whatever previous missions they were on. And so that's going to be all assembled in the coming weeks, I guess, and launch from there. Yeah.
Cool. And so what's the actual date of the launch?
So it starts on November 24th. Well, it's November 23rd at night here on the West Coast.
Cool. So, are you going to go? I want to go.
Well, I wish I could go, but I have to work.
Oh, right. You have to be there ready.
Yeah. So it's going to be a big day for us. We were actually doing a simulation today, which is basically it's going to last today and tomorrow. So we were simulating the whole launch and figuring out, how we're going to handle the different data, what can happen on the spacecraft after it launches, and how, what does that look in the data? What do we do? Who do we talk to? And so we kind of going over all of those simulations since the past couple of months.
But potentially launches like this from Vandenberg can be seen from LA on a clear night, right? Because Vandenberg's only like 120 20 miles away or something like that.
Yeah. If there's no cloud, everybody will be able to see it. And it's at night, so it should be very visible. The launch is actually at 10:20 p.m. here.
Oh, perfect.
Exactly. It's not even during the night.
Put it on your calendars, people. November, you said
23rd here on the West Coast at
10:20 p.m.
Yes.
Okay, so put it on your calendars. If you're in the LA area, Vandenberg Air Force Base is just past Santa Barbara on the 101, like another 30 miles or so. So yeah, you can look up to the north, well, I guess west by northwest probably, and be able to see this.
Yep.
Up into space. Cool. Okay, sorry, again, I'm hogging the questions. Let's see. How much of a change starting at the point of landing does the dynamic impact affect trajectory? What was the estimated trajectory? So I guess like you said that when it impacts Dimorphos, is that the name?
Dimorphos, yeah.
Dimorphos. When it impacts, it changes its velocity by a few percent, 1%?
It should be about 1%. So it was estimated to be about 10 minutes, and we're hitting it in the way that it should be the most visible. So it should kind of, slow down the orbit, if you want, by about 10 minutes.
Because it's hitting against its normal. So it's going like this, and you run into it, slowing it down.
A little bit, just a little bit. Yeah. And so we kind of hoping that exchange of momentum is basically what's gonna slow it down by probably up to 10 minutes.
Is there any rotation in Dimorphos at all, such that you're testing? Because one of the audience members brings up, Nikki Parafergan brings up, are you testing other things like the Yarkovsky effect, which is this differential rotation thing that you get from light reflecting off part of the reflective parts of the asteroid, and it causes it to rotate. So I guess, is there any rotation in the object that you'll be striking, or?
That's a good question. I'm not sure I remember this one. So I know a lot of the binary asteroids have, the bigger asteroid has like its own spin, and then the small moon is often kind of locked with the bigger asteroid, in the sense that it's just going to spin the same amount at its orbital period, kind of what the moon does with the Earth.
It's like tidally locked, kind of.
Right. Yeah. And so I think I can't remember if it was seen or inferred that it might have like a little wobble to it. But other than that, I don't think it's going to change the actual spin very much.
So it's mostly just test how well you conserve momentum in terms of like how much is transmitted to this, and if you can effectively change its trajectory at all.
Yeah.
Cool. Ashley Landquist asks how funding towards planetary defense strategies like this works, because obviously NASA is the major funder of this particular thing, but this is going to benefit, this is a baby step in trying to defend the entire planet, not just the United States. So is there alternate funding sources that are coming from different places, or the future of being able to do that? Or is it all just NASA's like, we'll take this one for the team, guys?
Yeah, I think it's been difficult over the past couple of decades, because, like the trying to map everything that's out there and trying to make that link in between asteroids out there and meteorites on Earth, and what kind of lands on us, what should we be afraid of? There've been a lot of effort and observations, but this is the first mission. And in terms of planetary defense and coordinating what countries should do, I think it's been difficult for countries to kind of own the problem. It's not really a problem that can be owned country by country. So I think that the funding, there's more funding now than there was, which is a good sign. And then NASA has put money in this mission. They've put money in the observation, a good amount in the past. And then HERA, this European mission, is funded by the European Space Agency.
I see. So it balances a little bit.
So yeah, so there's other fundings that are there, not just NASA. It's kind of probably starting a little more to be visible now.
What's potentially the next step after this? Is it to use a larger or a more high velocity impactor to hit, you said if this hit something that was just on heliocentric orbit, it would only change its period by like 0.000001% as opposed to 1%. So what's kind of the next step that you think in the next decade or 2 decades from now where we're moving towards like affecting the trajectory of potentially dangerous asteroids?
I think probably the next big demo will probably be this gravity tractor mission concepts, where you send kind of a big spacecraft to an asteroid, and basically by its presence and kind of hovering close to the asteroids, you can kind of slowly change the trajectory over a decent amount of period of time. And there's a lot of technicalities or difficulties in handling that on a mission level. And so that's, I think, probably the next big demo that we might see. And there was already some talk of doing that on some missions that got canceled. So I would think that that's probably the one that's going to come back. There's the kind of high explosive concept that's, depending who you talk to, it's popular. But that seems to be much harder to demonstrate, and that has a lot of political fallback to it.
You mean slamming something into it? And there was a related question about this from Sam Tung. It's just, you're just testing just the base level impact that it's making. There's no kind of additional explosive material, but that's what we're discussing. Like for a future mission might do that, but that's politically challenging because it has other,
right. So the
space is
in terms of when we see a threat, what we could do, it kind of depends when we see a threat. And so the kinetic impactor is kind of probably the best solution if we already have spacecraft concept, and we can make one, launch it if we have enough time. And if we know that in 20 years there's an asteroid that come in, we can slam something to it, change its orbit so that in 20 years it's just going to fly by Earth and not going to hit us, right? If it's closer, then you might want to do something else. And one of those techniques might just be to, send some high explosive and make the big asteroid smaller pieces so that if you're really going to hit us, then it's just going to burn in the atmosphere. And so, but that, I would invite people to look up planetary defense conferences, and they always have like a case study at the end of it, where they kind of have a simulation of some asteroids coming in, and they have people participate and figure out what they could do. And sometimes the best you could do is evacuate people, and some other time is to actually come up with mission design. And so there's kind of different cases that people can look at that are pretty interesting. But in terms of where the money would go in the next mission, it's kind of hard to believe that we would touch the high explosive one just yet, just because it has a lot of political impacts. And
absolutely.
Yeah.
Okay, cool. Well, thank you very much. Thank you for joining us, Julie.
Yeah, thank you.
Okay, I will bring on our next speaker, Dr. Ritabon Basu Thakur. Hello.
Hello.
Welcome, sir. How are you?
All right.
It sounded like, you were stressed today because there was a power outage, presumably induced by all of this rain that we've been having that caused some difficulties in the lab for you at Caltech, correct?
Yes, all our telescopes, as I'll discuss, are cryogenic telescopes that require a lot of power-hungry machinery behind the scenes, and one shuts off in a cascade, everything goes off, and you have to run in to save the day. Our students were on top of it, thankfully, so we made it through.
That's good. That's good. Oh, and speaking of save the day, you've got Batman in the background. That's pretty sweet.
Always.
Good superhero. I dig him. I like the fact that he doesn't have to rely on superpowers other than his mind and wealth. I guess he has wealth too.
We ask for a lot of funding for our projects as well.
Cool. Okay. I will introduce you and then we'll get started. So Dr. Basu Thakur is a postdoctoral scholar at Caltech and affiliate at NASA JPL. He received his PhD in particle astrophysics between Fermilab and the University of Illinois at Urbana-Champaign. His current research is on the BICEP array project, mapping the polarized cosmic microwave background from Antarctica. He's also the principal investigator for a NASA technology grant on advancing superconducting spectrometers for space applications. Both these projects are aimed at answering the question that bugs Rito in his sleep: how was the universe born? Outside physics, Rito is also interested in jazz and bagels. I also like bagels quite a bit. So it's unfortunately, do you know of any good bagel shops?
Yes, I live next door. I chose my apartment based on bagels.
Wait, where? Which bagel shop?
Bell's Bagels on York.
Oh, I have not been there. I will have to invest.
Well, Cameron, I'll treat you.
Excellent, excellent. Okay, go ahead and share your screen and take it away, sir. Thank you.
Yes. Okay. All right. Is this seen? Can you see this?
This looks great. Thanks.
Okay, excellent. Yes, so my name is Ritoban Basu Thakur. I'm at Caltech and I go by the name Rito since third grade. I work on telescopes that are in Antarctica with the singular goal of probing the universe right after the Big Bang via the earliest gravitational waves that existed. And so hopefully in the next 10 slides, you will see what all this is about. So a reference to Big Bang cannot be done in Pasadena without calling out the TV show, The Big Bang Theory. This is, of course, famous all over the world now. I mean, I remember watching it when I was in India. And in the show, the lyric, the Bare Naked Ladies have this beautiful song. It opens with, "Our whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. Wait." And so we should refer to what this all means in our attempt to understand the beginning of the universe. Jokes aside, the study of cosmology, or how we understand the evolution of the universe, has a very direct historical footprint here in Pasadena. So Mount Wilson, which I can see from my office, is where Edwin Hubble made this groundbreaking discovery, where he noticed that stars that are further away from us are moving faster. And this observation was, after the fact, supported by Einstein's theory of general relativity. And when Einstein was indeed visiting Caltech, there was this PR photo taken of him looking through the telescope as if they're doing real-time data analysis. This was not the case. This measurement of these stars that are further away moving faster directly imply that the universe is expanding, based on the statement that there is no central point to our universe. The so-called Copernican revolution and such things have led us there. So with that, we understood that the universe was expanding quite some time ago. And so if you now kind of play this game backwards in your head by saying, okay, so we are here now. I know there are all these stars and galaxies. And this is today. So if I now imagine time going backwards into the past, so that's for me going right to left in this picture, well, then all these objects are getting smushed together. That's contraction, or the opposite of expansion, which means that if you go really far into the past, everything is smushed really tightly together and things are bombarding with each other. And effectively, the collision is going to destroy anything. And so you end up with that famous lyric again from the song, "Our whole universe was in a hot, dense state." So that's sort of the paradigm of how the universe has been evolving. And we can add a little more detail to this. So now let's think of it in normal coordinates of the arrow of time going forward. So you start off the universe with this hot, dense state, again, based on the observations of Hubble and the theory of Einstein. So now in this hot, dense environment, everything is colliding so much that you don't have any stable atoms and everything is ionized. And in as much as you cannot see through a flame, right, the universe is opaque at that point, because any emission of a photon or a particle of light is quickly captured by an ion and then re-emitted and so on. So light doesn't travel in beautiful straight lines that it does today. So what happens is, as the universe is expanding, it is cooling down. This is pretty common sense, that you take a pot of boiling water, you throw it out, it spreads, it cools down. And so as it cools down, there exists a particular temperature, if you will, where the collision energy is not high enough, and the electrons and the protons can stabilize. They can form bounded pairs, which we call atoms. And in this early days in the universe, no stars, no supernovae. So these are simple atoms like hydrogen and helium. Now, when you have neutral stable atoms, light can travel. This is why you can see me through this camera. There is air between me and the camera, but light can travel through it because the air here in my room is neutral and stable, much like your room and anywhere else now. So as this light is traveling freely, this is sort of in the regime where the universe is transparent. So the first light that we get from this process, where the universe goes from opaque to suddenly transparent, makes for this omnipresent background of light today, which we call the cosmic microwave background. So you can think of it as the cosmic background of light. We tag on the adjective microwave because the color of the light is redshifted, from red to infrared all the way to microwave frequencies. But that's what we have, this hum of light, called the CMB. And there are other poetic monikers, such as the first light, the afterglow of the Big Bang, yada, yada, but that's all this is. So we have been measuring the CMB for a while now, and several space telescopes particularly have measured it over the decades with improving resolution. So in as much as your cell phone's camera resolution is changing by the decades, these space telescopes are also improving. So you can see in a patch of this map here from 1992 to 2013 how the information in the image is becoming more clear. You're resolving more structure, so to speak. And these structures, these red, blue, speckles, if you will, are sort of contrasts. They're false color images showing hot or cold. In essence, the CMB is really like looking into a cold oven. It's what in science we call the black body spectrum, very smooth, just like, a cold black oven, if you will. So it's kind of boring at first pass, but if you zoom into it, which is what these pictures are doing indeed, you can see that there at sort of a part per million, there are these hot cold spots. And so it's slightly noisy. Now, what's interesting is that this noisiness has a statistical similarity that is the same no matter where you look in the sky. When I say statistical similarity, what do I mean? Just an example or an analogy. So you may have a white noise, let's say you're relaxing by a river and the river is flowing and you have the trickling water noise. That's white noise. Or you can be, next to a busy highway. That's also another type of kind of quasi-white noise. Very annoying, not as relaxing, but that's what we mean by statistical similarity or dissimilarity, where there are noise, but there is a pattern in this noise that allows you to distinguish the two. In case of the CMB, again, if you look at directions on the sky that are far apart, so like say the North Pole and the South Pole, if you will, they look very, very similar, again, identical to, parts per million. And the question that we have here is, why is there this statistical similarity between regions or patches of the universe which are farther apart than light travel distance? So as you know, the speed of light is fixed in this universe, right? That's famously Einstein's discovery. And so if light has this fixed velocity or speed, then how could have information transferred between these two patches to make them look so similar or in equilibrium? So again, if you imagine you open the door on a winter day, you get a draft of cold air, but over time it comes to equilibrium because the air mixes. But here there is no option of mixing. They're so far away. So how come this is the case with our universe? And it's a very profound question in modern physics. And that's sort of what we are getting at here. How do we answer this question? So to answer this, a theory was proposed, a theory or a hypothesis, an idea, which says that, okay, what about this? So let's say right after the Big Bang, and in like record small times or quantum times, or Planck times, as we say, the universe rapidly expanded. So we discussed the Hubble expansion, which is a more smooth and gentle expansion. But what if there was something like this, but was, far more accelerated? Well, if that happens, then things that appear distant today would have been proximal back in time. They just got stretched out real fast and they appear as separated, but really they were connected, causally connected, as we say. So that's a theory. And the question is, can we test this theory? As you know, Karl Popper had the philosopher had the statement that a scientific theory is one that can be tested and potentially falsified. And the answer is, yeah, we can. We can, in fact, test it by relying on the cosmic microwave background itself, the thing that taught us that this could be a possibility, a feature of our universe. And so that's going to be the rest of my talk here. So to get there, I have to talk a little bit about gravitational waves. So this, you all may be familiar with famously the LIGO experiment detected gravitational waves or ripples in space-time from mergers of black holes, which got our professors at Caltech a pair of Nobel Prizes. And there are gravitational waves produced no matter what the source is, as long as there is some sudden change in energy with time. So they can be mergers like what LIGO detected, but they could also be produced by inflation, where space-time is rapidly stretching up. And in fact, there is this what we call a spectrum of gravitational waves. At the audio band or frequencies where you can hear it, you have events that LIGO would detect. But at very, very low frequencies, there's this hum, which you can see, so to speak, via the cosmic microwave background. And that's what we will talk about now. So again, you have this inflation, this rapid expansion of space-time. And this is, again, a rapid change in energy density with time, which sort of shudders space-time. And everywhere you have these ripples of gravitational waves just emanating. And then when the time progresses and this neutral atom formation happens and the cosmic microwave background comes out, these gravitational waves are still there. And they effectively alter the polarization of the light that is the cosmic microwave background. And this is polarization in the standard sense of your polarized sunglasses. And what we expect, the nature of this polarized signal is shown in this sketch on the left-hand side. What we expect are these swirly, curly patterns in the polarized CMB. And this can be generated only by gravitational waves. And gravitational waves are expected from inflation. So you can connect the dots here. So if I can detect such swirly patterns in the CMB, and I can measure how loud these patterns are, how intense they are, I can make a statement about how energetic the process of inflation was. And so it's a very general search probe, and it's a very clean search probe. And I've linked a paper below there, The Quest for B Modes from Inflationary Gravitational Waves. Very nice paper, to review paper, explaining it to college-educated people, how you can think about this. So anyway, so that's what we are after. How do we do this? So, so sort of the big pictures plural are shown here. So we do these searches by deploying telescopes in Antarctica, particularly at the South Pole. And there are multiple telescope sites as shown in that picture. All these bowl-looking structures are either ground shields or mirrors for these telescopes. And with these telescopes are measuring the cosmic microwave background from the very pristine and clean sky of the South Pole. And the type of image that we get, one of the latest images really, is shown on the right-hand side. And you're seeing a faint, swirly, curly pattern there of these so-called B modes of the CMB. And we expect the inflation-driven signals to be pretty faint, is something like 10 parts in a billion. So we are getting there. The current sensitivity of our telescopes is world-leading. In fact, we recently had a few press releases on Physics Today and so on and so forth about this, but we're not quite there yet. We're working hard to get there. And we expect within the next decade, we will have a very clear sense of what was the process of inflation by measuring these curly patterns in the B mode or the CMB. So, how do you measure it, right? Like, what's the tool? The tool is a telescope, and you can really think about this as a DSLR camera. So if you had a DSLR camera that you cut in half, like some guy did here clearly, it looks very similar to our telescopes. You don't need to read all the legends, but that's sort of what I'm making the association. So it's just bigger because we're looking at larger wavelengths, but the overall principle of collecting the light, guiding the light is pretty similar. Now, at the heart of it, we are measuring these photons, these low frequency photons, with very tiny detectors. And there are thousands of these tiny detectors packed into what we call the focal plane shown below. And if you were to zoom into that, you would see structures like this in the left-hand side here. These are some of the smallest superconducting circuits that JPL fabricates for our program. And so we are kind of utilizing these quantum technologies, the physics of the smallest scale, to poetically understand the physics of the biggest possible scale, the birth of our universe. And this all gets done with a lot of not only brain power and computer power, but muscle power. And so our team, the last team that I was part of that deployed one of these telescopes is shown here. And Caltech is the lead for the newest generation of these detectors and telescopes, along with the listed other universities. And so it's a group effort. And we are struggling through COVID. 2 of our students just went down to kind of take care of this telescope and upgrade it. And yeah, with that, I think I'll leave these summary slides and just sort of connect the dots for you. This may have been a lot. So we have this cosmic microwave background that comes from Big Bang cosmology. We have measured it. We understand it in reasonably good detail. And via our maps of the cosmic microwave background, we have learned that there must have been a process like inflation that stretched the universe rapidly. And this process would have generated gravitational waves. And we are trying to detect the imprint of these gravitational waves in the swirly polarization of the CMB. And our telescopes are built to be very, very sensitive. And over years, we expect to make very pristine maps of this polarization pattern and then answer the question, what happened right after the Big Bang in Planck time and quantum time? And with that, I'll take questions.
Excellent work, Rito. Excellent presentation. Great job to explain a difficult topic. All right, let's see. Questions from the audience. We have a couple. I encourage people to ask questions in the YouTube chat, and we will try to address them. And then we'll get started with the pub trivia in just a few minutes. All right, so why do you choose Antarctica as an ideal place for measuring the CMB as opposed to here in Pasadena?
Yeah. So that's a very good question, because if it were Pasadena, it would be much easier, right?
Much easier.
So let me put it this way. How do you heat your dinner regularly? You use a microwave oven, right? So that works because water absorbs microwaves, pretty efficiently and heats up, right, the food product. So if you have an atmosphere that is moist as humidity, then the microwaves coming from the cosmos will get absorbed. And similarly, the water molecules themselves will emit microwaves that will further confuse the signal. So you really can't see through it. And so the atmosphere is effectively not transparent in microwave. If you go to a place like Antarctica, so South Pole particularly is 10,000 feet high. So the altitude means you don't have that humidity, but also it's very, very, very cold. And so any water you have immediately forms ice. And so it's truly transparent in the microwave. And that's why it's a good site. Now, ideally, if we had a lot of cash, we would just do everything from space. And so this is sort of why we choose Antarctica.
Are there plans to have a space-based CMB or microwave mission at some point in the future?
Yeah, there has been a project called PICO that my boss Jamie Bach and then some other people have been leading for a while. So it's sort of in the plans, but I think once we see some hint of a signal from Earth, we will build the big telescopes and launch it in space. So that's the thought process there.
I see. So it's like, do the stuff from the ground until you can demonstrate it, and then everyone's like, okay, now it's worth investing a ton of money in. Exactly. Kind of like LIGO. I mean, LIGO has always had a decent amount of money, but now the world is going gravitational wave crazy because LIGO finally demonstrated after 30 years that gravitational waves are a reality.
Good analogy. Same business.
Cool. Do you guys need people? I want to go to Antarctica. Can I go and like do a winter over and take care of your mission? I guess
Oh,
it's
yeah,
not a
you
winter
can-
over. You guys do it during the summer.
Yes, but if you wanted to volunteer as a winter over, that's a highly sought out position.
Okay. All right. Well, I'll follow up with you afterwards. Um, so Genghis Galahad asks, does the thinning ozone affect observation? Like the history of like the ozone and all of that?
Yeah, not really. It's such, I mean, again, from Antarctica, it's a very small change. And it does like oxygen absorption lines do appear, but we choose, so like every camera can have a filter, right? Like a red filter, green filter, and so on. So I didn't talk about this, but we also have filters, and we choose those filters where emission lines from things like hydrogen, water, oxygen, so on are not present. So we avoid that from the get-go.
I see. Okay. So Andrew Reitemeyer asks, general question. Entropy means the universe will get more disordered over time, but I have a problem seeing the Big Bang as ordered. Is there a way to picture this in one's mind as the Big Bang being an ordered structure as opposed to later in time, we have a higher entropy and things are kind of smeared out?
So I'll pull out a book from my bookshelf here that I'm reading now.
Oh.
This book talks about this. It is not a very well understood problem what this person is asking, and Sean Carroll at Caltech is actually working on it real time to understand the dynamics of entropy over cosmic time and what that means. So that's sort of the big arc of me not answering the question. But to get to the point, you can think of this as order and disorder. Namely, as the universe is expanding, your ability to organize things in more different ways is increasing. So in some sense, that's a change in entropy versus early universe.
Because you have more volume in which to put all those different chunks.
Right, and the early universe is low entropy because everything is continuously scattering with each other, and in some sense, it's similar. It's so similar, it's so equal. So yeah, there is this question is quite important in modern physics.
Cool. So I remember early in the days of BICEP, there was the first big release, and then it was kind of met with some skepticism, and there was follow-up, and it seemed like the main result was not, in fact, primordial black waves, gravitational waves. It was due to dust scattering and those sorts of effects. Is it the hope that future missions will? How are you guys getting away and mitigating the effects of dust that might be contributing?
Yeah. So that's so I think I'll say one sentence sort of before this discussion. So the CMB is the first light. So that means we are seeing literally everything from now until that. So what, like the whole universe is in your way. Right. That's a challenge. If
a lot of stuff.
Yeah. If you're observing a star and whatever, a planet or this and that comes in, you can mask it, in analysis or even build a star shield. But if the whole universe is in your way, it's tough. So what do we do about it? Well, we use, again, the topic of filters or different colors. So we observe in different microwave bands, and dust, for example, is very bright at higher frequencies near a terahertz. And another thing called synchrotron, where the electrons are going around in the magnetic field and emitting more photons, radio frequency photons, is very bright at lower frequencies in what is known as the Ka band, 30 gigahertz or so. So what we do is we make multiple telescopes, each observing at different colors, and when we do color space analysis as well as image space analysis.
I see. Okay. That makes sense. A few more questions here before we move on, but some really good questions. Will the James Webb Space Telescope contribute in any way? Because that's operating in the infrared, but perhaps it's not going far enough into the microwave to be able to contribute to this sorts of research.
Yeah, so no, the short answer is no, it won't contribute for the reasons you just said. But there is a iota of a hope, and this is a topic, a pretty complex topic known as non-Gaussianity. So it is how clustered are galaxies in the universe? Does it follow the random normal distribution that we are used to, or is there something more? And inflation actually allows for some non-Gaussianity. And if you can probe that, you would be still answering the same questions, albeit indirectly and very statistically. So it can help, but not by a large amount.
Okay. James Young asks, LIGO has demonstrated that it takes very, very precise instruments to actually make these direct detections of gravitational waves. How difficult is it to do these detections of gravitational waves through the cosmic microwave background at very early times? It's a similar mechanism. You're looking more indirectly at the presence of the gravitational
That's
waves,
right.
as opposed to directly detecting them.
That's right. That's right. It's indirect, but nonetheless, the challenge is still present. And the first layer of complexity we have to bite through is what we were just discussing with the multiple colors, so that you are sure you're seeing the perturbations that really come from the inflation driving in the CMB and not anything else.
I see. Get rid of the foreground, only get the CMB itself.
Yeah, and again, here for us, foreground is the entire freaking universe. So it's a lot.
Does any of your research touch on, so Ben Riordan asks, does any of your research touch on events prior to the Big Bang, or is it just post Big Bang?
It's very hard to define what is the Big Bang. We can talk about, the expansion and, from that sort of, a process. So I think I'll go back to the same, Alan Lightman book and Sean Carroll's work. It's just hard to talk about before the Big Bang. In fact, there's a chapter in this book I was holding that's quite literally titled, What Comes Before the Big Bang? And it's not easy to posit even the questions. So I don't think this kind of research will directly answer anything like that, unless we find something, truly extraordinary. That's always a hope, but it's hard. I mean, we are intellectually limited on that kind of a question.
Yeah, it seems very challenging to ask those sorts of questions based on the current laws of physics.
Right.
Okay, I think our last question, Bretton Woods asks, inflation is a theory. How can we probe the inflationary aspect directly and with certainty? Because, how are the photons actually probing the inflatons in the inflaton field? Is it simply by the expansion and by the impact that would have on the CMB itself?
So it is not a direct probe. That's the short answer. The long answer is that, I don't know, either you or the audience asked the word inflaton, put the word,
I threw in inflaton.
Okay. So inflation, when we say, this rapid expansion is happening, what's driving it? The thing that's driving it, if you will, is called the inflaton for everyone. And the perturbations of the inflaton density is giving rise to gravitational waves, which we are trying to measure with the CMB. So you can see it's very much indirect.
It's like two indirect modes. It's looking at the CMB, so photons, that's probing
That's right.
the gravitational waves, which are probing the inflaton field.
That's exactly right. Yeah, but one can show from some, very, straightforward for us perhaps, but not for everyone, mathematics, that it's a clean probe. Even though it's, A goes to B goes to C, there aren't other paths in there. It's a very clean and pristine probe.
I see. Okay, great. Okay, one last question. I'll throw in one last question.
Yeah.
So Genghis Galahad again asks, are the cosmic microwave background's cold spots a clue to speculative bump against another bubble universe, or is it statistically normal in the overall heat distribution between like the cool and the hot spots?
That's a very interesting topic. In fact, we have a new postdoc at Caltech whose PhD was on this.
Oh, really?
Yes. So the cold spot, probing the cold spot. So as of now, it's pretty much statistically normal. But if you look at the what we call the power spectrum, i.e., how much intensity there is on an angular scale that is this narrow versus this big versus this big and so on, there is a anomalous dip, if you will, compared to what would be the standard, Gaussian distribution. And unfortunately, we have only one universe and one image. That's what we measure, and that's what it is. And it's hard to talk more about it. And that's where I would leave it.
Okay. Yeah, I guess it's hard when you have a sample of one.
Yes. Yeah, the comic book world of multiverses would be much nicer.
Right. Well, and it's similarly in the field of like trying to, people are always like, what's the probability that there's life out there? And it's like, well, we only have a sample size of one so far in terms of life is developed here on the surface of the Earth that we've yet discovered. So it's hard to say how probable or improbable it is to have developed on other planets. So even though there's like 10 to the 24 potentially other planets in the universe, it's hard to know like.
Well, but you still have a potential on 10 to the 24, which can reduce to a number more than one.
Right.
We have
right.
one universe. There is no way we are breaking through this.
Excellent. Well, thank you very much, Rito. Excellent presentation. And Julie, why don't you come back in? Now is the stage of the Astronomy on Tap that's devoted towards pub trivia for our audience. Basically what will happen is I'm going to share my screen and there will be a website that you can go to either on your phone or on another web browser called menti.com, and the questions will pop up there. They will also pop up on our screen, so you don't have to do that aspect of things. There's no charge. You don't have to sign up for something and you're going to get a bunch of spam. It's just a standalone website that the questions will pop up, you can respond, and then those responses will pop up on our screen in real time, and you can see how everyone is doing, and we can see like, how people are doing. So I encourage people to not cheat. Yes, you have the internet at your fingertips right now. We know you can look up the answer. Some of them may be really easy to look up, some of them may be hard, but what's the fun in that? If you don't know, that's okay. Put a BS answer. If you know, put the right answer, or if you don't know, make a guess, and we'll all see all the guesses that people have. So there's not really anything to be gained by cheating in this aspect. I'm not going to praise your knowledge or ridicule you and shame you for your lack of knowledge. So anyway, let me share my screen of this quiz. There are 10 questions. So, can you guys see that? Can everyone see that? Rito and Julie? Excellent. Okay, so in order to participate, if you want to, you could just sit here and watch this live stream and be like, oh, I know the answer, but I'm not going to tell them. In order to participate, you have to go to this www.menti.com and then put in this arbitrary number that's specific to our actual quiz. And then the questions will pop up. Actually, I was gonna grab my phone and go to this too and add in some bad answers so it's not too easy for people. Hold on, I'm gonna do that. Oh, I can't find my phone, so I'm not going to do that. So no bad answers to come through. Anyway, let's just go forward. The first question is, the Orionids meteor shower is currently happening as we speak. What is the source of the Orionid meteors? So people are free to answer this in their phones or in their web browsers. I think this is a word cloud, so you can put, is this from Jupiter? Is this from an asteroid? Is this from the sun? Is this it's from Orionid, perhaps. Maybe that's why it's named Orionids, because it's from the Orionid object. So go ahead and put whatever you think. You can put wrong answer. It could be from the Orion constellation. That seems reasonable. They're called the Orionids. That seems totally reasonable. So go ahead and put, we'll wait a few moments as people start to, the Oort cloud. Very good guess. Some comet or other. I dig it. That's where many of these objects and meteor showers come from, are some comet or other. Kuiper belt, yes. Orion. Any other options? Any other suggestions? Oh, Ritu, I saw you had a beverage. What beverage do you have? Oh, you're muted.
Very topical, Starburst IPA.
Ooh, that looks good. Who makes that one?
I have no idea.
Oh, okay. Yeah, I broke out another topical one called Plane or Satellite. It is a hazy double. Oh, my blurring is working. Oh, this crappy Zoom. Anyway, it's made by Bottle Logic. They're a really good brewery around here. I encourage people, if they are of age, Bottle Logic is a good brewery. It's good. Okay. Ooh, Halley's Comet. Comet, Shoemaker-Levy. Okay, all good options. Very good suggestions, people. The answer is this going to work? Let's see. Halley's Comet. So somebody got the correct answer. It is indeed Halley's Comet. Everyone has some familiarity with this idea. It's kind of the most famous comet. It comes every 75, 76 years. It was last in the inner solar system in 1986. And in fact, whoever put the Kuiper belt is also correct because that's where it sits when it's in the outer part of its orbit in the aphelion. So Halley's Comet comes into the inner solar system every once in a while, every 75 years or so. And when it does so, it, as you see with those comets, it starts to slough off material that gets burned off by the heat of the sun and the solar wind that blows off some of the ices that are exposed. But it also throws off some dust particles and rocks and pebbles that sit and they fill its orbit, much like you can see here. And when the Earth happens to pass through that kind of dust train in its orbit, those objects fall into our atmosphere and they heat up. Essentially, they're going super, super fast, like 50 kilometers per second. So, Julie, you were saying that DART is going to impact Dimorphos at like 7 kilometers per second. These things are traveling at like 60, 70 kilometers per second. So even faster. And when they do, they heat up the gas, the atmosphere in front of them and compress it. And it heats it to like, super, super high temperatures, like thousands of Kelvin, thousands of degrees. And it heats up the rock or the pebble or the sand grain, and then it vaporizes. And that, as it's traveling across the sky, that's how we see these meteors. And the reason it's called the Orionids, someone guessed, is because it appears to all come from the constellation of Orion. That's just like the direction of our travel into this trail of debris happens to be in the constellation of Orion. That's why it's called the Orionids. So the Leonids look like they're coming from Leo. The Perseids look like they're coming from Perseus. There's nothing special about, Orion's a cool constellation, don't get me wrong, but there's nothing special about it in this context. It just happens to be our direction of travel at the particular moment when this occurs. So anyway, you can check it out. It's not a spectacular meteor shower, even under the best of conditions. I was out in the mountains this weekend trying to see it, but it's full moon, so good luck. It's not great. You can only see, like, if it were a new moon, you'd see like 20 per hour, which is cool, right? But with the full moon, well, I didn't see one. Not a one. It's a bummer. The next big one, there's the Leonids, but they have a big moon. Geminids in December, they have a big moon. The next one that has a new moon are the Quadrantids right after New Year's, January 2nd, 3rd. So that'll be a good night to go out under a new moon and hopefully be able to see a meteor shower. Okay, who are the oldest 3 people to visit space? The final frontier. So who are the 3 oldest? Do you guys know? Julie, Rito?
I can make one wild guess, but that's it.
I know 2.
Oh, you do? Excellent.
Oh, wait. Astronauts? No, people in space.
Yes. Shatner, William Shatter Buzz Aldrin. Shatner. Okay. Buzz Aldrin. Buzz Aldrin is old, but he hasn't been to space for a while. Mr. Spock. Oh, I should have made this one so you could enter multiple ones. I'm sorry, I messed up with the interface, guys. Just put the one that you like. Star Trek dude is good. That's good. That's good enough. Shatner Gunk Glenn. Okay. Shatner Tully Mr. Spock. Some good options here. Good options. Glenn, Leica dogs are people. Yes, Leica, that's not the spelling, but that is true. Leica, the first the first dog in space. Dogs are people. Dogs are people. What's your dog's name, Julie? The one that was pining to get on camera throughout your presentation?
Nova.
Nova. Oh, I like that. That's awesome.
Yeah, for the 2 eyes, I thought the nova phenomena that we see in space kind of was fitting for her eyes being different colors.
Oh, she has 2 different colored eyes?
Yeah.
Oh, cool. That's so cool. Obama, one of the oldest people to visit space, according to someone. Excellent. Okay, well, many people did in fact get the eldest person to visit space, William Shatner, who just went up recently on a Blue Origin flight. There's him when he was youthful and him when he was not as youthful. So he was 90 when he went up, pretty impressive. Wally Funk, who has an incredibly inspiring story. She was one of the original, they're called FLATs, which stands for female, oh, I'm gonna mess this up. Female, it was like female astronauts in training in the 50s or in the 60s and 70s, and was meant to go up, but they ended up canceling it because NASA's a bunch of jerks. And so she didn't get to go to space until she went up with Bezos in Blue Origin just about a month or so ago. But she went up at the age of 82. But she's super awesome. And John Glenn, who was one of the original Mercury astronauts, who I think was the third, let's see, it was Alan Shepard and then I think Wally Schirra, and then John Glenn went up. He was the first to actually orbit the Earth, not just the first to go into space, and then stuck around. He went up a few more times, and he went up. They're basically testing the effects of space on old people. And so they were like, well, we'll let you back up because you're old and you already have experience with this. So he went up on one of the space shuttles a while back. But, oh yeah, there's a picture of him. That's not when he was that old. That's when he was younger. I mean, clearly not super young. He's losing his hair. But anyway, yeah, those are the 3 eldest people to have reached space. Although, so space is defined as like beyond, I think, 100 kilometers above the surface of the Earth. So Shatner and Wally Funk have done these suborbital flights that are just basically like a mortar going up and then coming down, whereas John Glenn is actually like orbited, and actually I think he was a Gemini. He may have gone as far as like orbiting around the moon and back. I don't remember his whole itinerary, but I don't think we've yet had in the age of modern private space flight. I don't think anyone's done any orbital flights. I think they're just suborbital thus far, but potentially soon we'll have orbital flights for space tourists. Okay, the James Webb Space Telescope. Everybody loves James Webb. Has arrived in what country, where it will be launched in a little over a month? Hopefully, fingers crossed. Ooh, French Guyana. Okay, some options here. Keep them coming. Maybe it's being launched from the Baikonur Cosmodrome in Kazakhstan, where all the Russian Space Agency launches its stuff. I don't see any Kazakhstans here. Maybe it's launched from, what was it, the Outback Steakhouse in the Maldives, which is one of the questions, or one of the answers that was provided by an audience member a few months ago. China, Guinea, Guyana, French Guiana, Outback Steakhouse, yes. The Outback Steakhouse of the Maldives. That's where I want to go. France, good, okay. All right, some good options here, everyone. The answer is indeed France. It's tricky, right? Because French Guiana is not actually a country. It is a dom-tom. It is a department outre-mer. It is part of France that extends into South America as a relic of colonialism. But for all intents and purposes, it's kind of its own country. So that is why that's where the primary European Space Agency launch site is in South America. It's right here in French Guiana in South America. And the reason that's chosen, a few reasons actually. It's really close to the equator. The equator is just below the bottom edge of this red box going through Ecuador. So it's only like 6 degrees above the equator. And that provides a few benefits. One is that as the Earth rotates around, you get more of a kind of a fling outward if you launch close to the equator. That's why we have Cape Canaveral in kind of the southernmost part of the United States in Florida, as opposed to up in like Maine or Minnesota or something like that. But it's also beneficial because it's directly west of the ocean to the east. And so when something launches, all the junk that gets spit out, you know, the hydrazine, as well as like if there's any bolts that fall off this thing, drop into the ocean and not into somebody's backyard, because you don't want that. Nobody wants a bunch of hydrazine falling on their shed in their backyard, right? So this is the site where it's going to launch. And basically all the European Space Agency launches take place from here, which is kind of wild. Pretty, yeah. That's an illustration of Old Glory here, James Webb with its beautiful gold-plated mirrors. The gold wasn't just chosen because they were really looking for bling. It was gold because it's really reflective in the infrared. Anyway, okay. If an asteroid, ooh, I like this one. If an asteroid is on a collision course with the Earth, what could we do to mitigate its impact? Lots of things, I suppose. Some of the things that Julie discussed. What do people think about this? I need my phone so I can look at what people are discussing. Hit it. Hit it. Gravity tractor. Detect early. I prefer hit it. Just give it a punch, you know, really. Damn it. Blow it up. Nuke it. Black paint. Okay, okay. Launch explosives the Armageddon way. Yes. Ask it politely to leave. That works in some contexts, you know. Somebody's roughing you up at a bar. Just ask it politely to leave, to vacate the premises. Paint it white. Sunlight. Oh, it even rhymes. I dig it. Transport it. Run away. Indeed. These are some. This is great. Thank you, everyone. Send Captain Kirk. Captain Kirk to save the day. He can use the transporter on it. Leave Earth. We could just run away and avoid it, or let it hit Earth. Yes. Okay. Lots of good options. Lots of good options. Many of them viable. Oh, a gentle nudge. Ooh, just give it a little nudge. So one of the options, there was a paper recently that was put out about the possibility of dealing with an impactor where we only had, you know, a few days notice, like a week notice. This is coming right at us. We're totally hosed. We got to get rid of this. We can't rely on some of the technologies like Julie was discussing in her presentation, where we can modify its orbit by a little bit. Because remember, Julie, you said, how much are you modifying the orbit of this object by slamming this object into, by hitting it with DART? You're only moving it, you're changing its period by 1%. And that's only in its orbit around Didymus.
Right. Yes. So just 1% around the bigger asteroid, but just it's like, you know, very small compared to, it would be very small compared to this sun.
Right. So if this thing's flying at us and it's barreling down at us and we send something up to hit it from the side, we're not going to be able to affect its trajectory very much if it's already on a collision course with us, right? So,
Yeah.
so this paper was discussing the idea of pulverizing it, essentially sending a bunch of rods with explosives into it so that it breaks it up. And even though those will still be heading towards us, it's not a single impactor. It's like broken into a lot of different little chunks So the idea here, like on the bottom panel, you intercept it, you break it up so it's kind of, the outer parts of that cloud that's heading at us even miss the Earth, but you're spreading out that impactor over a much larger area. I mean, it's not great, right? We don't want to get hit by all this crap, but at least it's not like a single impactor that's really gonna be super bad.
Yeah, I think if it's less than like 10 or 20 meter in diameter, then it should just all burn up in the atmosphere. It might do like something that happened in Russia, if people remember, like
the Chelyabinsk
Chelyabinsk impact, I guess, or I'm not sure how we call it, but Chelyabinsk.
Yeah, I think that impactor was like 30 meters or 25 meters or so, and so it had a shockwave that knocked out a bunch of people's windows, but it wasn't like this fireball that destroyed a city or anything like that.
Right. So I think when it gets to like, I'm used to speaking metric, sorry.
That's okay.
When it gets to like 100 meter or 150 meter, then that becomes more problematic. And then you kind of you might not be able to do much about it, but maybe you can move people away from the impact. So yeah.
Indeed. Oh yeah, and that's roughly the premise of Armageddon. So I mean, it's obviously different, right? They go up there and they're like, and they messed up a bunch of science in that movie. It's not that great of a movie. I'm not a big fan, but they went up and tried to basically put explosives, well, a nuclear bomb, but explosives in the interior of the thing and then blow it up. So again, it was like it was dispersing it instead of a single impactor. But I guess that's potentially a viable solution.
Yeah. There's a lot of things that didn't get right and scientifically in that movie, but I watched it somewhat recently, I guess 5 years ago, waiting for another big milestone to happen on a mission. I'm not gonna get into the details of that, but it involved watching Armageddon on the big screen at night, waiting for a mission to land somewhere, and trying to stay awake in the middle of the night in critical time, right? So we watched Armageddon on the big screen in the mission control, and yeah, it was so very funny to have a bunch of navigation people watch this movie and just hear all the things that they got wrong. But it was a very good movie.
Cool. That's cool. Okay. Next question. What determines the expansion rate of the universe at any given time? So this is a multiple choice. Inflatons, dragons, the Hubble constant, and the current component of the universe with the highest energy density. Looks like Hubble constant. Oh, we've got one for dragons. Excellent. Some Game of Thrones fans out there, D&D fans. Inflatons. What do people think? Hubble constant is winning. Okay. Any other answers before we go to the, inflatons jumps. Nice. Still only one for dragons, you guys. Disappointing. Seems like the overwhelming victor here is the Hubble constant. What do you think, Rito?
I am, really impressed. Statistically speaking, given this is a histogram, the answer is exactly right. Because it is the Hubble constant, but the Hubble constant, is largely determined by the dominating component of the universe at that time. And very long ago, it were inflatons. So, amazing show of response.
Excellent. So I made this slide to kind of demonstrate how that changes over time. Do you want to discuss this a little bit?
Sure. Yeah. So, like the answer or that was posited before the Hubble constant is sort of the thing behind this picture. So as cosmic time goes forward, what dominates the universe changes. So before the CMB, it was radiation dominated, namely the energy density of photons or light really controlled how the universe was expanding. And then after that, you're in this matter dominated period where things like dark matter, or basically us, normal matter, dominates it. And then, close to today, where your graphs just like eke into the green zone, there is this mysterious new thing called dark energy that's, popping up. And if you were to run this way back, inflatons would indeed be the right answer. I'm not sure where dragons enter here yet, but yeah, great answer set.
Yeah, perhaps after dark energy will be the dragon.
Age of dragons after dark. Yes.
Okay. Last month, the NASA Lucy mission launched into space to eventually study what objects? Do you guys think? Lucy. It was all over the news. $1 billion mission launched successfully. Whoa, Jupiter Trojans. As opposed to Saturn Trojans, Earth Trojans, Venus Trojans. Meteors, okay. Lucy. Asteroids, things in space, moon. Well, I do like the moon. I'm a big fan of the moon. Asteroids. Other options, any other suggestions? Heavenly bodies, indeed. Some good options. Okay. Looks like people were virtually all, I think almost all of these answers are correct, except I'm sorry, Moon. I love you, Moon, but not this time. All the other answers are correct. So it's largely trying to study the Trojans, the Jupiter Trojans, and how it does that. So just for reference, the Trojans are these objects that are in orbit around the sun, just like the other planets in the solar system, but they tend to sit in these stability points called Lagrangian 4 and Lagrangian 5 points that are these semi-stable points in front of and behind Jupiter in its orbit. So essentially, if something kind of falls in there with the right velocity, it'll just kind of hang out. It's almost like a little, you can kind of, if you envision the gravitational field or space-time is like the surface of the Earth, these are kind of little valleys, little pools where stuff is just going to kind of collect and not move around too much. And the Trojans that are there appear to have, they're a bit like the asteroids. And so it'll be really interesting, but they're farther out. So it'll be interesting to see what characteristics. Nobody's ever gone to visit one of these or study one of these. It'll be interesting to see what kind of characteristics these have. Are they rubble piles? Are they stony? Are they icy? What are their characteristics and what's their composition and what's unique about their behavior and their orbits? This is a nice time lapse of the Lucy launch from Cape Canaveral a couple of weeks ago. Oh, and this is a nice little video showing the trajectory of the spacecraft on its way to get to the Trojans. So green is the Earth orbiting here in the inner solar system. In brown is Jupiter. This isn't a Jupiter-centric view, so it's not moving. And the blue is the spacecraft. So it's going out and it's going to visit. These white dots are the actual objects that it's going to visit. So those are some of the Trojans. Again, this is L4, the Trojans that lead orbit of Jupiter, and this is L5, the Trojans that fall behind. Oh yeah, it passed by this guy, which is in the asteroid belt itself. And so what's cool about this mission, I mean, aside from the fact that it's going to visit Trojans for the first time, is it's visiting like 8 different objects in its orbit, which is the most objects that have been observed by a single NASA mission. Even Voyager didn't do close passes on like 8 objects. It was like 5 or 6 objects. So it's really cool, and it's going to visit all these guys in the next 20 years or so. Because space travel is slow. It takes a long time to do that business. Speaking of space travel, what is the mass fraction between DART, what we heard about in Julie's presentation, double asteroid redirect test, and its asteroid target? How much more massive is the asteroid that this mission is running into versus its mass itself? Because we gotta launch this thing, and it's gonna be, it can't be infinitely heavy. It's got to get there. So what is the mass differential? 42. That's always a good answer when it comes to numerical questions. Good one, person who did that one. 42. So what is it 42 times heavier? Is it or rather, is the asteroid 42 times heavier? Is it 100 times heavier? Is it a technical term, Tinsy? Is it 1,000 times heavier? Is it a gajillion times more massive? 1 million. Dr. Evil responded with that one. About 350. I dig it. People are getting into it. 100. Technical term, Tinsy. 1 out of 1,000. Pi, another good numerical response, regardless of the question. Maybe we'll get an E. Pi, less than 1/100. Okay, some good options. All right, let's lay into it for Dr. Julie Belrose.
Yeah.
Julie? Yeah.
1/10 million. So in that one chart, there was the density of the whole system, which is kind of the most likely density of the two asteroids. And then you had the diameter of each of them. So if you remember some basic maths, volume of a sphere, say, as a good approximation, 4 pi r cube over 3. And then times the density, and you get to the mass. And then the spacecraft mass is about 650 kilograms. So it's about 10 millions to 1.
Wow, 650 kilograms. So it's like 10 people's worth of mass. This spacecraft. I mean, I guess it depends if it's like 10 fat Americans or if it's like 10 people from the rest of the country, or the rest of the world. So it's like 10 people's worth, 15 people's worth of stuff. And then wait, so that object, that Dimorphos, was like 300 meters in diameter or something. So it's just a big chunk.
Dimorphos is 160 meter in diameter.
160 meter. Okay.
Mm-hmm.
Wow. Okay.
Yeah. So just put 10 big people, just smash them very fast.
So fling them into a football field in half and see what happens.
You're gonna move this thing. There you go.
Yeah, not very much. Okay. Okay, cool. Thank you. All right, Castor and Pollux, the twin stars of Gemini, are featured in what blockbuster film? Blockbuster film, yeah. What do people think about this one? Normally I have a Star Wars question, but I was getting kind of tired of Star Wars questions. So I figured I'd switch it up for this classic blockbuster film from the when was this? Late 1980s, early 1990s, if that provides some hint. Castor and Pollux. If you've seen it, you probably remember. So we've got Contact and we've got Armageddon and Dune. Ooh, Dune just came out. Has everybody seen Dune? I have not yet had the opportunity to sit down and watch it. I'm hopeful. I'm a little bit wary. I really like Dune, the book. I think it's one of the best science fiction novels that's been written. But there's so much interior monologue. I'm worried that they're going to muck it up. But I've heard pretty good things.
Apparently, it's a masterpiece. And if you know,
really?
So Denis Villeneuve is the director.
Sure.
And he's done great things so far. And yeah.
The Blade Runner follow-up, he did that. And
Yeah.
but you're biased, you're Quebecois. So of
Yes.
course you're gonna love the French director.
He's from my home country, yeah.
Have you seen it yet?
I have not. Yeah, I can't wait to go see it. Yeah.
So yeah, Jaws. It's not Jaws. That's a good guess. Jason and the Argonauts, Armageddon, Face Off, Contact Dune, Pokemon's Vacation. I have not seen that masterpiece, but I will add it to my list. The answer is indeed Face Off. A really melodramatic film from the late, I feel like it was early 90s, featuring John Travolta and Nicolas Cage. So let's just go to the astronomy aspect of this before we discuss the film, the cinematography aspect of things. So Castor and Pollux are the twins in Gemini. And you're like, oh yeah, that looks kind of like some twins. I mean, more than most constellations look like the thing that they're supposed to look like, right? But without the lines, it's hard to fit. Like, that doesn't look like some people. That's just a bunch of stars. I mean, yeah, okay, I can make out like, oh yeah, maybe that's the waist and these are the legs. But it's hard, right? So it's hard to just identify these stars in the sky. What I use to figure out Gemini is basically look at Orion. Orion is like the most identifiable thing in the sky, right? You've got that belt. That's pretty bright. It's pretty easy to see. And then you've got Betelgeuse, big old red guy here. So if you basically do, you find the belt and you go perpendicular to the belt and go up, ta-da, those two bright stars are Castor and Pollux, which are Gemini. So then you can be like, hey friends, that's Gemini. And then you sound like you know what you're talking about. But what's interesting is Pollux is actually the brighter star. But in the film, the Castor, who's played by Nicolas Cage, who's super, super melodramatic, is definitely the brighter character. It's kind of a crummy movie, but it's kind of good for being as bad as it is. So I encourage people to watch it if they have an opportunity. It's a John Woo film. He's a really good director, good action sequences, but yeah. You got to look at Nicolas Cage being kind of crazy. Let's see. Light pollution is a concern for people wishing to view astronomical objects. What is a growing source of light pollution that we haven't had to deal with in the past? What do people think here? Starlink. Okay. Fireflies. Yeah, those are really blocking our view of the sky. Street lights, LED lighting, satellites, mobile phones, everybody holding their mobile phones up in the sky, causing a little bit of sky glow. Satellites, city lights. Indeed. Lots of good responses here. Okay, maybe that's as much as we're going to get on this one. Indeed, all of these responses are very good and are viable. Drones, sure. Internet satellites. I chose to focus on based on the results of a paper that came out in the last few months that basically suggests that mega constellations, these Starlink is an example of one of these mega constellations of satellites, but there are a number being developed by, Jeff Bezos, Elon Musk, other tech billionaires who want to put a lot of things into space. Sure, it's problematic to see the individual satellites, but even when you can dim them so they aren't visibly bright to your eyes, there will potentially be enough of these that just increases the surface brightness of the sky. So even when you're out in the middle of nowhere, so let's say you're in Death Valley, or you're on a boat in the middle of the Pacific, even if you're at what would be considered a dark sky site, there will be enough of these in the sky, and if things go according to plan in the next 20 years, that they might not individually be bright enough to see by eye with your naked eye. They'll just contribute to the overall sky brightness and make it like you're living in a city. So you won't be able to see the faint dark, a dark sky sight from anywhere on the surface of the Earth, because there will be enough of these just scattering enough light that it increases the sky brightness, which sucks, right? I mean, it really sucks for astronomers who really want to look at faint stuff in the sky, but it kind of sucks for everybody. Like when you look up in the sky in a city, you're like, oh, wow, I can see like 12 stars. So you want to go out to, some dark sky site like a national park and see stuff. But even if you can't go there and see dark sky stuff, it's not so great. This is a video of one of the Starlink trains right after it launched. So essentially Starlink launches a bunch of, Starlink is SpaceX's internet service provider thing, where they have a bunch of these satellites that go up and are on these orbits, so that wherever you are on the surface of the Earth, you can get internet. Yeah, it's a little bumpy here because it's just an amateur person taking photographs of this. But these Starlink trains, they put them up and they start their orbit, and they're all in a single line, but over time they kind of diverge to spread out over the sky so that you get reasonably uniform coverage of the sky. Well, this is giving me a little vertigo here. But yeah, there's going to be, I think SpaceX is planning to put something on the order of 10,000 Starlink satellites in the sky, and similar numbers from Blue Origin and some of these other large companies, space flight companies and aerospace companies. So it's unfortunate. And there's a lot of efforts being done by the American Astronomical Society and increasingly the International Astronomical Union to try and hey, can we mitigate this in any way? Can we paint them black so they don't reflect as much light? Or can we do something to make it so it doesn't have as much of an impact on the resource, this natural resource of the dark sky? But fingers crossed that changes at some point in the future. Ooh, I got a thumbs down on that question. A thumbs up and a thumbs down. I guess maybe there's a Elon Musk fanboy in the audience who's like, ugh, SpaceX at all costs. Screw you, astronomers. Oh yeah, this is an image. If you were to take a long exposure image of the stars, this is what you would see. You'd have all these satellites passing through your field of view, and you'd get a bunch of nice lines on your image. Not so great. Ooh, 2 thumbs up on that one. That Musk hater, or that Musk lover left. Okay, how long will the Apollo astronaut footprints naturally remain on the surface of the moon? This is a multiple choice. Several different options here. So the Apollo astronauts, if you believe it, I believe it. I think there's plenty of evidence that suggests that, oh, okay, there we go. Plenty of evidence that suggests the Apollo astronauts did. In fact, we had 6 missions that visited the moon. They walked around on the moon. They left some nice boot prints there. How long will those boot prints remain there before they get disturbed or wiped out by natural processes? Forever? 1 billion years, 1 million years, 1,000 years? They're already gone? Or Apollo was a conspiracy, ! 11 in all caps. Good. Okay. Nice little Gaussian distribution here. This is good. What do you guys think? Julie, Rito? What do you guys think? Don't worry, I'm not going to shame you if you're wrong. I don't know if I'd know the answer off the top of my head.
I voted for 1 billion years.
Mm-hmm.
I figured that, it would be, there's practically no atmosphere on the moon, right? So it's not going to be weather.
It's not going to be wind that's that blows it all out of the place.
Right. So the most likely cause would be some asteroid that would kind of fall nearby, and then there's maybe some small meteorites now that falls on the moon, but it might take
a while.
To actually wipe out the print. So
I agree. What do you think, Rito?
think there's a non-Gaussianity here. There's a rare event. Yeah.
That's true. Got some
Rare events.
kurtosis to this distribution.
So I would say, instead of probability density, I will answer with a cumulative density and say it's more than 1,000.
Okay, I can agree with that. I can agree with that. The answer is roughly 1 million years, less time than Julie predicts, but that's okay. It's not like we've been around 1 million years or 1 billion years to see them kind of dissolve. But based on current rates at which we think the moon is being impacted by objects that could kick up material, you're right, there are no surface processes like wind or water that would naturally erode this. The main thing is due to other impactors, meteoroids and asteroids that are impacting the surface of the moon. So this is actually a really cool image that I like that was taken with the Lunar Reconnaissance Orbiter that's orbiting around the moon and shows the actual, this is Apollo 12's launch or landing site. So you can see the footprints, which is super cool. And you can see the actual descent stage. Obviously the lunar module is no longer there because it had to take them back up, but you can see essentially their path on the surface of the moon. And that'll stay there for a really long time, which is pretty awesome. Yeah, so essentially, when you look at the moon, you see a bunch of craters, but if you zoom in, it's like craters all the way down. And the only thing that disturbs the existing craters is the production of more craters from more impacts. And that time scale is on the order of 1 million years. But this is actually used to date different features on the moon. If you look at an area and you think it has fewer craters than a neighboring area, then it means that it's usually younger in its surface renewal or surface processes because it hasn't had enough time to regenerate from additional impacts, which we think at this point is generally kind of uniform in its distribution and in terms of its impact rate. Oh, you've reached the end of the presentation. So that's all we got for the that's all we got for the pub trivia. Congratulations to all of you guys and your phenomenal submissions. Thank you for participating. And yeah, I'm sorry I don't have prizes to send to everyone. Hopefully, so we're looking to start redoing these in person at some point. Probably January if COVID abates a little bit more. It's just not ideal. Our events at the Wolf had like 150 people shoved into an area that was, officially allowed to have 100 people in it, according to the fire marshal. So that's not really good for COVID transmission during a global pandemic to have people like crushed against each other, breathing on each other. And I didn't want to be responsible for some sort of outbreak in the Pasadena region. So the plan is when things get a little bit more under control, we will go back to in-person events. We're probably not going to hold them at the Wolf since there have been a bunch of brawls there, barroom brawls. And I don't want neither the astronomer guests who are speaking nor the audience who's coming to see these events to get stabbed. Nobody wants to be stabbed. I don't want to be stabbed. So I'm looking for a different venue, but hopefully in the new year. When I do, I'm going to do all I can to make sure we stream these or record these so they continue to be available online on YouTube. But stay tuned. Hopefully in the new year, we'll have these events in person again. I think that's all I got. Our next event, 1 week, all in Spanish, all about James Webb Space Telescope and the science that's being done with it. The week after that, again, all about James Webb Space Telescope, but it's in English. And then we'll have another James Webb one in December, right before the launch. Well, hopefully the launch in December. I forget the exact date. You guys know? It's like December 16th, December 17th.
Yeah, 18, I think.
18th. Okay.
But someone should double check that.
Indeed. Well, Julie, Rito, thank you so much for your presentations, for joining us tonight. Very much appreciated. I learned a bunch in both of them, and hopefully our audience did too. Thank you, audience members, for joining us on a Monday night and partaking in science. And hopefully we'll see you guys again next week if you speak Spanish, or in a future coming week. So thanks, everybody.
All right,
Have a good
thanks,
evening.
everyone.
Thank you. This was fun.
Yeah.
Good night.
Good night.
Very good.